can we predict the future? In other words, is nature sufficiently deterministic? And can we know the underlying laws so that we can compute the future as well as the past? Very famous scientists from the 17th century onwards, like Galileo, Newton, Laplace, they all said yes. But around the turn of the 20th century, there was a famous French mathematician, Henri Poincaré, who said no. Already in 1903, Poincaré wrote the following.
Il peut arriver que de petites différences dans les conditions initiales en engendrent de très grandes différences dans les phénomènes finaux. Une petite erreur sur les premières produirait une erreur énorme sur les derniers. La prédiction devient impossible et nous avons le phénomène fortuit.
Although Poincaré originally discovered the sensitivity to initial conditions, it took the American meteorologist Edward Lorenz to make this clear to the rest of the world. In 1964, Lorenz started to perform a series of computer experiments using a simplified model of the weather. To his astonishment, he noticed some very disturbing phenomena which everybody using computers and calculators should make very worried. I will redo these experiments using a simpler equation which exhibits the same phenomena. The equation is the following. X of n plus 1 equals a times x of n times 1 minus x of n. Now, this equation is equivalent to many other similar equations, such as the logistic equation proposed by the Belgian mathematician Pierre Verhulst for modeling biological populations and their development. It's also similar to a very important equation that will show up in fractal geometry, which was developed by Benoit Mandelbrot, which is the equation z goes to z squared plus c. Now, I'm going to iterate with this equation, which means that I'm going to plug in specific values for a and x of n, and then I'm going to compute x of n plus 1 and plug that back into the equation, and that way keep reiterating. So let me use the value 1.4 for a and 0.3 for x of n. So this means that for 1 minus 0.3 I get 0.7, and for 1.4 times 0.3 I get 0.42. Now when I multiply these I get a value of 0.94. So when I plug that back in my equation, I can compute the next value for x of n plus 1. Now this procedure is a little bit tedious, so I've written a computer program to perform this kind of iteration, and we're going to do a little experiment with it. In fact, I've done it 2 times. Once for the value x1, which will keep going up, and the second time for the same value x2. And I'm also going to compute the difference between x1 and x2. So let's do this now, and let's do it for, run the experiment for 10 time steps. These are the values that we get. So we started with 0.3, and in the third column we see the difference here. And so you see at the end of the time series we get a certain value, and because the values are the same, so the difference stays equal to 0. And this is exactly what we would expect. Now we're going to do an experiment. I'm going to slightly change the precision of the second value, namely x2. So I'm going to say change value x2 so that it's almost equal to the other value, to the one we had so far, 64073. So I leave out the last digit, which is 9. Now we're going to iterate again for another 10 time steps and see what's happening. So initially we started with a difference of 9, but what we see is that the error between the two, that means the difference between x1 and x2, is gradually becoming bigger and bigger. Now this is known as the virus of unpredictability, because the error is growing exponentially, so there's an exponential divergence of the 2 time series, even though we started with a very small difference between the 2 quantities originally. To visualize this effect even better, I'm going to plot out now the values of x1 as they evolve in time the values of x2 and also the difference between the two. So let's do this for another 50 time steps, let's say. Okay. What you see that at the beginning, the error here is very small, but as we go on here, suddenly, well, the value is starting to increase, and if I keep going, let's say for another 30 time steps, we see that the value becomes almost as big, well, in fact, as big as the original values that I have here. So I will now let it continue to go on for another 1,000 time steps or so. But what we see here is that the error, which was very small in the beginning, is now becoming as big as the original time signal, which means that there's no relationship anymore between the two quantities. When Lorentz saw an effect like this, using his own more complex equations, he was astonished. Was there something wrong with his computer? He redid the calculation on other computers and calculators having essentially the same effect. He found that when you do the same calculation on two different computers even, you can get different results. Apparently, something very strange is going on. Lorentz called these phenomena manifestations of chaos, which he defined as follows.
Chaos occurs when the error propagation seen as a signal in a time process grows to the same size or scale as the original signal.
This is indeed the case in our example, because we can see here that the difference between the two quantities is becoming as big as the original time series. Now note that chaos is not the same thing as complete disorder. Lorentz gave the word chaos a new, more precise meaning. Chaos means apparent randomness in a system which is completely governed by deterministic laws. For scientists, randomness means anything that can ever happen can happen next. For example, if I toss this coin, the chances that I will get head or tails are equal. That means if I keep doing this and I make a set of data, then about 50% will be heads and 50% tails. Determinism is usually thought to be the opposite of randomness. Determinism means that only one thing can ever happen next, and therefore the system is completely predictable. A good example of this is the pendulum. The pendulum is completely described by Newton's laws. So if I have a movement like this, and I know all the coefficients, like the coefficient of friction, I can completely predict the state of this particular pendulum in the future. Now, the strange thing about chaos is that you get, on the one hand, determinism, and on the other hand, you get unpredictability. You have determinism